Okay, good afternoon, and lecture, what is it, 11? 11? Good. All right, so a couple of announcements. I re-recorded lecture 5, which I uploaded to YouTube and wherever, and I didn't say that, which is online, but lecture 5, Zoom crashed in the middle, and so the screen wasn't visible, so you couldn't see what I was writing. So you could hear my voice. So somebody pointed it out. I've forgotten who, but anyway, I re-recorded it. So and it will be up on YouTube by the end of this class because it's uploading right now. All right, so let me get my last the last notes. Okay, so what we did last time was I introduced the renormalization group as a way of looking in a systematic way how the Hamiltonian of a system transforms as you coarse grain it. And what we saw, by the way, if you want to shut the door or just leave it ajar so you don't freeze. So what we saw was that as I changed the scale continuously, or through a sequence of coarse graining transformations, leave it slightly open so that if somebody comes in late, they can get in. There's a little doorstop on the floor. As you do a sequence of coarse graining transformations, the system will flow in the coupling constant space. So what you do is you start off with your Hamiltonian, you write down all possible terms that are consistent with the symmetry of the problem. So in the language that we were using, all the possible local operators that you can construct from your underlying degrees of freedom, and then multiplied by a coefficient which we call the coupling constant. So I write out a general form for the Hamiltonian. You might just start off with the nearest neighbor Ising model with only one term. But what we saw was that in general, as you do coarse graining, you will generate new terms. You will undergo a trajectory in Hamiltonian space. And we started looking at some of the mathematical properties of these transformations. And at the end of last time, we had a little in-class exercise where you tried to figure out what would happen to the partition function of the system and whether it would increase or decrease under scaling. And what we discovered after doing an explicit calculation was that, in fact, the partition function is invariant. And to do that, what we had done was we had written down a formalism in where we, if you look here on the screen on the left, we had our original original Hamiltonian in terms of microscopic variables SI. We introduced a projection operator that would have the following properties. If I choose a coarse grained configuration S prime, and I specify the coarse grained values, then I sum over all the possible microscopic configurations, and only those configurations that are consistent with a coarse grained description that I have imposed will give me a factor of 1, otherwise I'll get 0. And then when I do that, that gives me something which I called e to the Hamiltonian n prime, that is the coarse grained Hamiltonian, and we discussed its properties explicitly using the majority rule renormalization group transformation. So there you take a block spin that has an odd number of microscopic variables. You define the coarse grained variable SI prime to be the sign of the sum of the spins in the block. So I take my block, I take the sum of those spins, I'm going to get a number that is either going to be positive or negative. I take the sign of that, SIGN, and either get +1 or either -1. And so I get my block spin variables. And then I can keep doing that transformation over and over again. And so the way you construct a projection operator is just by putting in a Kronecker delta that has the properties that if the sum of the sum of the microscopic variables equals the coarse grained variable that you have on the left-hand side, SI prime, then you get a 1, otherwise you get 0. And we saw that that projection operator has various properties, and then from those properties, we deduced at the end of last lecture that therefore the partition function is exactly conserved. And it all makes sense, because all we're doing when we're making block spins is we're saying we're going to sum over all the degrees of freedom to compute the partition function, but we're just going to do it in a different way than we did before. Instead of going through every single degree of freedom and summing over all the possible states that it can take up, we're putting them into macroscopic configurations and then looking at the states that all of those can take up. And so we're just summing the possible states of the system in a different order. Okay, so what we want to do today is I want to explain to you what is the origin of singular behavior and tell you what the physical interpretation is of fixed points. And we will then start looking at renormalization group flows, literally the behavior of the renormalization group transformation in the vicinity of a fixed point, where we can linearize the nonlinear renormalization group transformation, but still preserve the important information. So let's get started with that. So the first thing I want to do is we saw how the partition function transforms, but what about the free energy per spin? So the next question I want to ask is, how does the free energy per degree of freedom transform? So you might say, well, the partition function stays the same, so the free energy would stay the same, but that's not quite correct. Because remember, it's the free energy per degree of freedom. And so the free energy per degree of freedom I'm defining to be 1 over n times the logarithm of the partition function of my original coupling constants. But after I've done the transformation, I now, one coarse grading transformation, I now have less degrees of freedom. So I can write this then as L to the D over n, L to the D. So I've just multiplied and divided by a factor of L to the D, but now I'm going to replace Zn by Zn prime as a function of K prime. So because those two things are the same. And so this then I can write as L to the minus D times 1 over n prime times the logarithm of Zn prime of K prime. And n prime is just n divided by L to the D. And so what that tells me then is that my free energy scales as 1 over L to the D times G of K prime. Okay, so there's a factor of L to the D that comes in there because I have less degrees of freedom. Now, why is the renormalization group transformation useful? This is a really fundamental philosophical perspective. Everything I'm going to say now applies to all versions of the normalization group, ones that you do for phase transitions, ones that you do for non-equilibrium phenomena, ones that you do for differential equations and fluid mechanics, and all the other ways that people like me and others have generalized over normalization group. So the basic thing about it is that we've taken a problem which requires summing an infinite number of degrees of freedom, or going to a system with an infinite size, which is what we have to do if we're going to look at a phase transition. We've taken that problem to break it up into small bits, do a small part of it, and then do that small part many, many times, infinite number of times, in fact. Now, why is that better? Well, everything we're doing is about approximation theory. And the way to think about what renormalization group is, I'm presenting it to you as if it was something to do with statistical mechanics. Okay, it has nothing to do with statistical mechanics. Okay, at the end of the course, I'll give you a lecture where I show you that. Okay, renormalization group was discovered in the context of statistical mechanics and quantum field theory. It has nothing to do with those things. It is about approximation theory. That's why you can apply it to solving differential equations and things like this. Okay, that's the if you like, the novel insight that is in my book compared to other books on renormalization group. Okay, so the statement is this: if I'm having to do an approximation of, say, a function over an infinite interval, or approximation to work out the thermodynamics of an infinitely large system, doing approximation theory over an infinite domain is very difficult because functions tend to either blow up or go to zero or something like this. And so you have to have extremely good approximations in order for them to actually converge and be useful. On the other hand, if I can do an approximation over a finite interval, over a finite number of degrees of freedom, over a finite time, over a finite regional space, that's easy to make very accurate approximations. And then when I do the infinite number of iterations of those transformations, what I'm going to be doing is using the very accurate approximations I've developed for the finite region and then extrapolate it to infinity. So that turns out to be much easier to do than to just do the whole thing in one go. So the basic idea of RG is the following. First of all, when we construct our renormalization group transformation, so I start off with some coupling constants and get an image, which is some nonlinear transformation of those. What we have done in doing that is this is a sum over a finite number of degrees of freedom. And if it's a sum over a finite number of degrees of freedom, that means it's analytic. Has no weird singularities. It also means it's easy to approximate. And so we can construct it in any way we like. When Wilson invented the renormalization group, he didn't know how to construct renormalization group transformations. He tried for several years to try all sorts of different methods to construct RG transformations. Eventually, they all end up giving you the same result. Some of them are more computationally feasible than others. But the point is, the thing they have in common is it's easy to make approximations. So that's the first part of it, is that you're summing over something that's finite, and so it's easy to approximate. And then you get the singular behavior by doing an infinite number of RG transformations. Because you're doing an infinite number of finite analytic transformations, that can give you singular behavior. But it's singular behavior that you have approximated very accurately. It's a very accurate approximation compared to the alternative, which is calculating singular behavior directly in the thermodynamic limit. But there's no small parameter as well. So that means that is the fundamental reason why this idea turns out to be useful. So the conventional picture is calculate the partition function and take n to infinity. And the RG picture is calculate RL of k and then iterate n goes to infinity number of times. So let me give you an example of how this actually works in practice. So I'm going to give you an example of how to get non-analytic behavior from an analytic transformation. So the example I'm going to think about is a particle in a potential well. In one dimension, just for simplicity. So I'm going to write down the equation of motion. X dot is minus dv by dx, like that. And we can think of then x as being some particle position. Okay, so let's draw the picture of what the well is supposed to look like. So here is x, here is my potential, and I'm going to, hopefully I'll draw this not too badly. So I'm going to draw my potential like that. And so let's ask ourselves what is going to happen to the particle if we start at different places. So let's suppose, for example, that I have my particle and it starts off here. So you can see that it's doing damped motion. So it's not obeying Newton's equation of motion. Mx double dot is minus dv by dx. It's got some damping. So we're going to think of this damping as being large. Let's think of this as being overdamped. Okay. So what's going to happen is if I start over here, then the particle will sort of gradually roll down this potential well until it gets to this point over here. Okay, so I'm going to call this point x sub a, and if I started over here, for example, then the particle would roll down the hill and eventually it would end up, say, over here at this point, which I'm going to call x sub c. And if, on the other hand, the particle were to start off over here, it would roll down and eventually end up at xa. If the particle were to start off here and roll down the hill, it would end up at position xc. So I could then draw on the horizontal axis the position of the particle. So I'm going to draw the picture something like this. Let's get a different color, like this. So the particle starts off over here, and then it moves downhill like this. So it goes like here, and then eventually it stops at the origin. If I were to start over here, my trajectories look like this. If I were to start over here, my trajectories would look like this. And again, over here, they would start like that. And then at the top, well, at the top, there's another fixed point. So the particle, if you started exactly, say, right at the top there, at that position xb, it'll just stay there forever. Okay, right at the top, it will never move. So that will stay there. And so then if I go back and draw my flows, they look like this. And we call this pattern over here, we call this pattern a flow diagram. Okay, so that is the behavior of the system, and these points over here where it stops, these here and here, all these 3 points, we call these fixed points. And you can see that the fixed point at xb, the flows go away from it. The fixed points xa and xc, the flows go into it. And so we will call this, for example, will be called an attractive fixed point. This will be an attractive fixed point. This one over here is a repulsive fixed point for obvious reasons. Okay, so that's great. So now let's ask ourselves the following question. If I have this fixed point, I want to know then what is the map of the particle position as I go to different times. So I'm going to draw here, say, the initial behavior of the system. So let's call this x, which is x at t equals 0. And then on here, I'm going to draw what happens after I've done a renormalization group transformation by a finite amount of time t as a function of the initial condition. So let's then label our axes. So we know that xa, xb, and xc are fixed points. So that's going to happen over here. Sorry, the axes are different dimensions. That was a bit stupid of me. So I have something like this. I could draw these lines out here to guide the eye. Like so. Okay, so that's the picture. So what I want to draw first of all is what is going to happen when t is a finite number. So it's going to start, say, at this point over here. Let's say somewhere between xa and xb. If it started exactly at xa, it would just stay there. If it started exactly at xb, it would stay there. If it started exactly at xc, it would stay there. So we know that those are fixed points. They don't transform. If it started slightly to the right of xa, then it would go to a slightly if it started to the right, it would go to a slightly smaller value than it would have done if it had stayed the same. So if I draw if I draw a dashed line through here like that, so what will happen is if I start to the right here, instead of going to the same place, I'm going to go to somewhere lower. So I'm going to get a curve that looks something. Well, why is it doing that? Is this some great feature of GoodNotes? I didn't know. So this graph anyway here is meant to be what would happen when t is less than infinity. Okay, so on the other hand, so it's moved some distance. On the other hand, if I were to take the time to infinity, then what's going to happen is this curve is going to get flatter and flatter. So eventually, it's going to be like this. Anywhere I start in here in the interval x between xa and xb, at long times I will end up at xa. So it's going to go like that. And then anything to the right of that, I'm going to end up at xc. So this function will then be a discontinuous when t is equal to infinity. And the non-analyticity is this discontinuity. Exactly at xb. So what we can say is that the long time behavior of the particle position. I make this thing go away. What is, why is this happening? Okay. Okay. The long time behavior of the particle position. Does somebody have a computer here you can look on Zoom? And I haven't shared with you the Zoom link, have I? I just want to make sure that Zoom hasn't just crashed.
I think it's still recording.
It's still recording, and yeah, but it did that last time, and then something weird happened. Okay, well, if it's necessary, I'll just re-record this lecture, I guess. So the long-time behavior of the particle position is a discontinuous function of the initial condition. So this is what I mean by non-analyticity. But any finite transformation from an initial condition at time t to a later position at time t plus some delta t, that transformation is completely analytic. So this graph over here, I said this was t equals 0, but this could equally well apply for any time t to any time t plus some delta t, where delta t is finite. So this is a picture of the map. This green curve on the left-hand side is the renormalization group transformation that takes you from the position at time t to your position at time t plus some arbitrary t. And then the infinite number of iterations of that will give us this discontinuity. So this is the non-analyticity. And we see that there is different behavior. So if x is greater than xb, then that region is the so-called basin of attraction. Of the fixed point xc. So what that means is anything greater, anything to the right of xb will flow into xc. And then we have that x for x less than xb, and that's the basin of attraction of the fixed point xa. So this in this picture here, the time evolution in the flow is equal to the scale evolution of coupling constants during successive renormalization group recursion relations. Okay, so now, so what is the important aspect of this? So now I want to talk about fixed points. I want to talk about them in a little bit more detail because I want to look at the dynamics near the fixed point. Do you have a question?
Yeah, a question.
Yeah, go ahead.
So here the coupling constant, is it just the force?
It's the position.
It's a position. I see.
Okay, so let's see why that is. So let's suppose, so we're going to suppose that there are fixed points. So what do they mean? Well, my normalization group recursion relation says I start off with some coupling constants K, and I do some renormalization group transformation at scale L, and then I get my image of that under K. So that's just like starting at some position here on the x-axis, and then moving to a different position under this time evolution transformation. So the time evolution is like the renormalization group transformation. Okay, so what is a fixed point? So if I have a fixed point, what that means is that it transforms into itself. So let's have a look at what happens to the system, a statistical mechanical system, when I do this. So we know that under a renormalization group transformation, we know that the length scales get reduced. We know that the correlation length changes and gets reduced by a factor of L. That's why we know that when you do a renormalization group transformation, you move further away from the critical temperature. So we can say that if I look at the correlation length for the system after I've done a renormalization group transformation, then that is the correlation, the original correlation length divided by L. So if I start off with some coupling constants K, I do a renormalization group transformation, it scales the system's size by L, so that the correlation length has got smaller. Because the correlation length has got smaller, that means that I've moved further away from the critical temperature. Okay, so you knew before, but now what happens when we're saying this at a fixed point? So at a fixed point, psi of k star is equal to psi of k star divided by L. And so that means that the only solutions to this are psi of k star is equal to 0 or infinity. Those are the only ways that can be solved. If it's 0, this is called a trivial fixed point. And the trivial fixed points have a physical interpretation, as we shall see. They correspond to the bulk phases of a system. When the correlation length is equal to infinity, we know what that means. What does that mean?
We're at the phase transition.
We're at the phase transition temperature. So we're literally at the critical point. So this we call a critical fixed point. This physical interpretation is that you're at the critical point. I love the way that my pen goes all wobbly as I get to the right of the screen. No idea why. Who knows? One can know how to solve turbulence and physics problems and all sorts of things like this, but being able to figure out how an iPad works is sort of like the last frontier. All right. So do you have a question, Frank?
No, just hypothesizing why your pen.
Oh, okay. So we can do the theoretical physics of the computer game that is my iPad. But so okay, you're going to take my iPad apart and you're going to lecture. Great. All right. So if you give me some renormalization group transformation, then in general that will have several fixed points, maybe even an infinite number. Each of those fixed points have their own basin of attraction. And they will reach those fixed points only after an infinite number of iterations. Okay, so now we know that there's two types of fixed points. So now we're going to discuss obviously we're interested in the critical fixed points. So now we're going to look at the properties of critical fixed points. So here's a theorem, I suppose you can call it. I'll just be pretentious and call it a theorem. The theorem is that all points that are in the basin of attraction of a critical fixed point, so I'll call that CFP, have infinite correlation length. Okay, so how do we know this? Well, let's suppose I have a physical system, say some magnet, and it has some coupling constants K. Then after n iterations of the renormalization group transformation, then I'm going to end up with the nth iterate of all of those coupling constants, which I will write like this. So you can imagine then that I start off with my system with coupling constants K, and I compute the correlation length of that system. And then I do my RG iteration. So the first one gives me L times psi of K1, first iteration. Then I do the second iteration, L2 psi of K2, and so on and so forth. And then eventually I do n iterations. So I have L to the n psi of K of n, like so. And now what's going to happen if I take the n goes to infinity? Remember, L is greater than 1 by definition, and so that implies that the right-hand side goes to infinity. And that's true. That's true if psi of K infinity is a critical fixed point. So that means that that if the initial starting point describing the system, coupling constants K, were in the basin of attraction, of a critical fixed point, then that means it has an infinite correlation length. So you may think, well, wait, so what? Well, that's actually kind of profound. So let me draw you a picture. So we're going to call the basin of attraction of the critical fixed point. We're going to call that the critical manifold. Okay, that's just a name. So let's draw the critical manifold. And of course, I'm going to draw it terribly badly. So there's my critical manifold, and this is a manifold in my space, which is this sort of multi-dimensional, in principle, infinite dimension space. So here is the coupling constant direction K1, K2, K3, K4, K568, and so on and so forth. So that's my my space. I have a critical manifold which is in that space. So that's this thing that I've drawn over here. Let me try to make it look more manifoldy. So something like that. And then somewhere in that, on this is a critical manifold. So somewhere in here, there is a critical fixed point. So here is that critical fixed point. And then my flows in this space, those flows are, you start off from anywhere in this critical manifold, and anywhere you go, you do the renormalization group transformation and you flow into here. Okay, you start over here and you do your RG transformation and you flow into here. And you start over here and you flow into here. Okay, so that's what I mean by the basin of attraction. But each of these physical systems, this one over here, this one over here, this one over here, these circles are sets of coupling constants, and therefore they describe different physical systems. So as an example, you might say that this, let's call this 1, 2, 3, 4. You might say system 1, it's those values are the coupling constants that corresponds to, let's say, the nearest neighbor Ising model. Okay, it's the thing we know and love. Okay, system 2 might correspond to an Ising model with nearest neighbors plus next nearest neighbor plus next nearest neighbor. Well, I've just repeated it. N, next nearest neighbor. Number 3 might be an Ising model with next, I don't know, 137 times 130 Ising model, etc. And all of these, so these correspond to different systems, but it's not just that they correspond to those systems with arbitrary values. All of those things have the values of the parameters adjusted so that they are at criticality. So the important thing for each of these systems one, two, three, etc. For each of these systems, the coupling constants of the 137th nearest neighbor Ising model, the coupling constants are adjusted so that the corresponding model is at its critical point. So this is the basic explanation for universality. It's not the full explanation, but it's part of it. So this says, if I take, let's say, the 137th nearest neighbor Ising model, and the next nearest neighbor Ising model, and the nearest neighbor Ising model, if I adjust the coefficients so that they're tuned to be exactly at the critical point, they will then flow to the same critical fixed point, and that same critical fixed point is the reason why, because it's the same critical fixed point for all these different models, it's why these different models behave the same way at their critical point. So the RG picture of explanation for that is, this is the underlying reason, not the full reason, It's the underlying reason for universality. Because we can coarse grain these models these seemingly different models each with their special parameters that place them on the critical manifold and the infinite number of RG iterations moves them to the same critical fixed point, which somehow controls the non-analyticity of their phase transitions. Now, I haven't told you how the properties of the critical fixed point control the phase transition properties. We're going to get that a little bit later, but this is part of the reason for universality. Okay, so here's a question for you. Why do I say this is part of the reason for universality and is not the complete reason for universality? Because you might say, well, this is it, right? They all flow into the same critical fixed point. So of course they have the same critical behavior. So problem solved. That's not true. Why not?
We don't know why they flow.
Could you say it again, please?
We don't know why they flow to the same thing.
We don't know why they do. Well, we do because we've said that we've started off by saying all of these particular coupling constant values lie on the critical manifold. So there is a basin of attraction for this critical fixed point. And so if I choose systems that lie on that basin of attraction, they all may be very different physical systems, different, nearest neighbor rising model, 137th nearest neighbor rising model, with different values of the parameters, 100, 374, whatever. They all, we've said by assumption that after the normalization group transformation, they all flow to the same critical fixed point. And we also know that every point on the critical manifold has an infinite correlation length. So when we're looking at these systems, we know that if I was just looking at that microscopic system in the lab, and I was just building it experimentally, like you want to do, if I measured the properties of that system, I would find that it is at a critical point. It's undergoing a phase transition. Okay, so hence the question. So the logic of what we've talked about, the logic of this dynamical systems picture implies that all of these systems will have the same critical behavior, which sounds like we've explained universality, but I'm saying it's not the full explanation. So what part of universality have we left out, do you think?
It's like the existence of multiple critical fixed points.
So you're saying what?
Like you could have multiple such bases for multiple different.
You could, but let's just keep it simple for now. Let's just talk about one critical fixed. There's something very important that we haven't that you haven't thought about. Okay, let me try to when we talk about the critical exponents, that we derive for, say, the mean field Ising model, right? Alpha, beta, gamma, right? Those critical exponents. Okay. What question did they answer? So let's talk about the critical exponent beta. What question did that answer? How magnetization depends on reduced temperatures, that we said. Yeah. So it says M goes as Tc minus T to the power beta, and we calculated that beta was a half. So it tells you about the behavior as a function of T minus Tc. What about the critical exponent gamma? So somebody else, not you. So while you guys are looking at gamma, why don't the people on this side of the room tell me what the critical exponent alpha describes? With what? Did you answer the question?
Said it's for free energy. Like,
Alpha is the critical exponent of what thermodynamic quantity? And gamma is the critical exponent of what?
Gamma is for understanding the
heat
Susceptibility.
yeah.
So what is it? So what does it tell you? It says the susceptibility goes like what?
It tells you that it's it tells you that it's we calculated was the inverse of the little t minus tc over TC.
Right. So the critical exponent gamma says that T minus the susceptibility goes like T minus Tc to the minus one. Well, in mean field theory. Okay. And what about the other one? What's the other one? Alpha. Heat alpha heat capacity. Okay. So all of those things are those exponents describing the system at criticality? No, they're not.
Near, but not at.
What?
Near, but not at.
Near but not at. Close but no cigar. Yes. Right. They're near it, but not at it. And so so you might want to know what happens at criticality. Give me an example of an exponent that tells you about what happens exactly at the critical temperature. Delta. Yes. What does delta tell you?
Didn't that tell you how m scales as a function of t at the no as a function of h at the critical temperature? Yeah.
Delta. M scales like h to the 1 over delta. That's right. And that's the exponent that I call the breakdown of linear response theory, because normally the m would be proportional to h, but in fact it goes like h to the 1/3 or something like that in mean field theory. Right. So that's one that is true exactly at critical. There's one other one that goes as critical that you've known about. I've told you. And do you remember what it is? Eta, yes. What is it? What exactly? What does eta tell you? It's about correlations, yes. It tells you if I look at the 2-point correlation function at Tc, that goes as k to the minus 2 plus eta. And whatever. So there are exponents that happen at Tc, but most of the critical exponents tell you how things behave as you get close to the critical point. Okay, so the reason that it's only part is because we are interested in singular behavior close to, but not at the critical point. As an example, C goes as T minus Tc over Tc to the power minus alpha. Chi goes as T minus Tc over Tc it's the minus gamma, etc., etc. So these ones are T is not equal to TC. And of course, there are ones that are exactly at TC, and we want to know those too, but it's not, so this is telling you about something to do with the system, but not quite. So the basic point is, so we have to think about what happens off the critical manifold. Okay, so what we're going to do is we can't study the behavior everywhere, that's too hard. So what we're going to do now is look at the local behavior near but not at the critical manifold. So you had a question?
Before we go ahead, I wanted to ask, I don't think I fully understand how we got that if all of the systems on the critical manifold have an infinite correlation length, and what does that mean? I think it's for like, I don't really understand what that means.
Okay, so it's really, so the question was, how did we get this thing? So the basic point was, first of all, I'm going to say that you're on the critical manifold. Okay, so that means that under RG iteration, you will flow into the critical fixed point. And we know that the critical fixed point does have an infinite correlation length. So my argument was, shown here on the left-hand side, was that if I start off with my initial value k, after one RG transformation, that, remember, what happens is psi after RG, one RG transformation, is the original correlation length divided by L. So psi then is the transformed correlation length multiplied by L. Okay, so now, after one RG transformation, I've got to K1. After two RG transformations, I've got to K2. And the correlation length in that case for K2 is psi of K2, which is going to be the original correlation length divided by 2 powers of L, right? And so if I do an infinite number of those, then I get psi of K is equal to L to the N times psi of Kn. And then as we know that by assumption, we're on the critical manifold. So when I take n goes to infinity, that my coupling constants flow to the critical point, the critical fixed point. And the critical fixed point has a correlation length of infinity. And so therefore, going back through this chain of equations, the original correlation length also had to have an infinite correlation length. Because L is greater than 1, so you can't say, well, it's something like 0 times infinity. It's not like that. L is also greater than 1. Psi is going to infinity. L is 3 or something. So psi of k is equal to some number, which is actually infinity, times psi, which is also infinity. So it's infinity squared. Right? Did I answer your question?
What does this mean? Or like, what does it imply?
It implies what I just said, that if I start off with my initial points, which correspond to different physical systems with different parameter values, but all of those physical systems, the nearest neighbor Ising model, the 137th nearest neighbor Ising model, all of those systems, if you put them in the lab and measured their correlation length, you would find that they had an infinite correlation length because they're on the critical manifold. And they flow towards it, and they flow to the same critical fixed point because they're on the same basin of attraction of the same critical fixed point. So they will have the same critical exponents, supposedly, at least the ones that correspond to criticality. So did the penny drop?
I'm confused because I'm thinking about temperature here, where I'm thinking
Don't think about temperature. Temperature is just a parameter. Remember that the coupling constants are J over KT. Okay, so I don't care about temperature. You know, J over KT is equal to 1.753 or something. Okay, that's the magic number that will make the physical system be at its critical point. Okay, all I care about is the coupling constant. So I've absorbed all my factors of T and TC, because I'm near TC, into my coupling constant. Okay, so did I answer your question now? All right, perfect. Okay, so we need to think about the behavior of the critical point. So the next topic that we're going to look at is exactly that. So we are now going to look at the local behavior of RG transformations near a critical. Okay, so what we're going to basically do is the idea is this. So let's take our coupling constants. They're basically a set of vectors. Okay, one coupling constant for each of the local operators. Let's choose the nth one. So I'm going to say that I'm going to write that as Kn star plus delta Kn. Okay, so basically what I'm saying is I've got my vector of coupling constants. It could be a finite number, it could be a countable infinity, it could be an uncountable infinity. Okay, so I've got my coupling constant, and I'm writing this as K1, K2, dot, 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 Kn, dot, 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 like that. So that's what I mean by that notation. It's just a bad notation for a possibly infinite dimensional vector. Okay, so I took at the nth component of that, the critical fixed point, K star, is equal to all of those things, but with a star on them. And then I'm going to linearize around that critical fixed point. So each component of my coupling constant vector will have some perturbation that tells you how far you are away from the critical fixed point. Okay, so Kn star is the component of the critical fixed point for the nth coupling constant, whatever that might happen to be. Okay, all right. So then that means if I'm thinking of it like that, then basically my starting Hamiltonian is also close to the critical fixed point. So I can write that as H is equal to H of K star plus some delta H, and this thing over here I could call H star. So that's my picture in Hamiltonian space. And so now we're going to ask what happens after we do a renormalization group transformation. So I'm not on the critical manifold. I could be, but I'm not. It's specifying that. I'm just near the critical fixed point. I'm now going to ask what happens when I do a renormalization group transformation. So what's going to happen is my original vector of k's now transforms into some function, k prime of those. So I look at the nth coupling constant. It'll transform into a new variable, Kn prime, and this new variable, the new coupling constant, depended on the old coupling constant, so the previous step, and I'm going to write that as Kn star plus now a new delta Kn, a new deviation away from the critical fixed point. So this is delta Kn up here. This is the deviation from my critical fixed point. And after I've done a renormalization group transformation, I now have a transformed deviation. It might have got bigger, it might have got smaller. We don't know. We're going to find out. So then what I'm going to do is this thing over here is in general some complicated function. But what we're going to do is, because we're looking at local behavior, local means that we can linearize this function. So how do I linearize that function? Well, I'm going to just linearize it by doing a Taylor expansion. So I've got my k n prime, and that is a function of k1 star plus the new plus the deviation, k2 star plus its deviation, and so on and so forth. And this is some function of all of these things. And it's a horrible, messy, nonlinear function. But I'm going to just do an expansion of that. So I'm going to just write that as kn star plus dkn prime by dkm summed over m evaluated at the critical fixed point times my deviation delta km. Okay, so I take all the partial derivatives of this function. It depends on k1, k2, k3, all the way up to however many there are. So if I want to know how the nth component transforms, it will be some linear combination of the Taylor expansion of this multivariate function. So I've got this function, which I don't know. I take its derivatives with respect to all the km's multiplied by delta km, and that is this function. And then I have higher order terms, km squared, which I have neglected. So that's got to be the shape. That's got to be the general form of what this function will look like. And I don't know what this thing is, but I can write this in the following way: delta k n prime is equal to the sum over m delta km plus higher orders that I'm going to neglect. So there's some object here. This dk prime by dkm evaluated at the fixed point is just a set of numbers. They're a matrix. They've got two indices. So this is some matrix. So this is dkm kn prime by dkm evaluated at all the k's are at their critical value. So that's what this thing is, and so it's just a matrix. And you might say, okay, well, this is really simple, but it's not necessarily simple, because this matrix doesn't have to be symmetric. It can be a very complex matrix, and we don't know what it means. So let's have a look just geometrically at what I've just written down. So let's suppose I draw my infinite dimensional coupling constant space like this. So there's my coupling constant space. Let's suppose that over here I have my critical fixed point. Let's suppose that over here is where I start. So I start over here. So this is the critical fixed point. So this distance here is the vector that I've called delta k. It's how far away I am from the critical fixed point when I start. And then what I do is I do a renormalization group transformation. And under that renormalization group transformation, this thing now becomes, let's say, delta k prime, like so. And so this point has moved so now what's happened is this point has moved from here to here like this. And so this is the renormalization group transformation that has happened. And so I can map out a trajectory which, as long as I stay in the vicinity of the critical fix point by looking at this linearized dynamics. So what we say is that M is a matrix, is a linearized renormalization group transformation. So when I write down KL, K prime is RL acting on K, then this is a nonlinear function. And what we've done is we've linearized this. So yeah, we still have a bit of time, a few more minutes. Okay, so the next thing that we need to do is we need to explore the properties of this matrix. How do I make this thing go away? What the heck is this? Okay, so we need to explore this. Okay, so okay, so first thing about M is it's not symmetric. There's no reason why it should be in general. So that means that its eigenvectors are not orthogonal. And it means that I have different eigenvectors depending upon whether the vector is to the left or to the right of the matrix. So I have left eigenvectors and right eigenvectors. And also, M is not diagonalizable. And lastly, the eigenvalues are not necessarily real. This is really bad news for physicists because the only linear algebra that we know is done from quantum mechanics. And in quantum mechanics, everything is symmetrical, everything is Hermitian, everything is orthogonal, everything is, well, everything that you learned in quantum mechanics is of absolutely no use in studying a renormalization group. Okay, so I want you to know this, and in my book I explain how you deal with this, but we're going to pretend that none of this is true. Okay, so we're going to look at examples where it does happen to be symmetric and real and all of this stuff, just to get the basic formalism. The extension of it to being non-orthogonal, non-symmetric, blah, 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 that's actually really easy. Okay, so it's just a page in my book. I don't want, it's not the important part of the story. It's a technical aspect of it. So the next thing that we need to talk about, and I don't think I want to start it today, is what we're going to do is we're going to, our strategy to explain this view, our strategy is going to be, one, we're going to pretend that M is symmetric. And the reason we can get away with that is, even though it's not true, is it is the extension to non-symmetric is easy once you've got the basic idea. Okay, so we're going to see that. Okay, so that's the strategy. Then the next thing we're going to do is we're going to expand the RG transformation near the fixed point in terms of eigenvectors of the matrix M. And we're going to look at the physical significance of the eigenvalues of it. So what we're going to see is that we're going to have different types of eigenvalues. Some of those eigenvalues are going to be positive, some are going to be negative. The ones that are positive will mean that as I expand in those eigenvectors, I'm going to, after RG transformations, get closer and closer to the fixed point. On the other hand, if those eigenvalues are greater than 1, and after successive RG transformations, I will go along the corresponding eigenvector away from the critical fixed point. So what we're going to see is that our trajectories in the vicinity of the critical fixed point actually are dominated by the physical directions where there's eigenvalues that are positive, that are growing, not shrinking. And so what we're going to do is next time we're going to classify our dynamics in terms of the eigenvectors. So we're going to do an expansion, and then we're going to see that the things that matter are these growing eigenvectors. And what we're going to see, in fact, is that because those eigenvectors push you away from the critical fixed point, and you want to know what corresponds to the variables that you control in your physical system, like temperature and field, those are the variables that you control to get you out to the critical fixed point. So what we're going to see is that that corresponds to starting in a way that you don't have any eigenvectors perpendicular to the critical manifold. In other words, you're on the critical manifold. So the critical exponents are going to end up being related to the eigenvalues of the linearized renormalization group transformation. Okay. So that's what we're going to see next week. Okay, so that's it for today's lecture.